morning class and welcome to another lecture in sustainable energy technology. Today we will start our discussion on geothermal energy technology, where we are sourcing the heat that is present in the interior of the earth and using it for electricity generation and heating applications. Before going into the details of geothermal energy, let us discuss what is the status of geothermal energy production in the world today. Geothermal energy can be used to generate electricity or use it as process heat or hot water applications. In 2021, around 99 terawatt hours of electricity was generated from geothermal sources, and the total installed capacity worldwide was 14.5 gigawatts. This is a small but significant fraction of the total renewable electricity that is being generated in the world today. The growth of geothermal energy has been modest over the last few decades, with around 0.3 to 0.5 gigawatts of capacity addition on average on an yearly basis. If we look at the country-wise distribution of where geothermal electricity capacity is installed, we will see that a few countries like United States, Indonesia, Philippines, Turkey, New Zealand, as well as other countries like Mexico, Kenya, Italy, these countries have the majority of geothermal electricity generation capacity in the world, while the rest of the world put together contribute only a small fraction of what these countries individually generate. This shows that geothermal electricity generation is very unevenly distributed in the world, and this is a result both of lesser emphasis on exploration of geothermal reservoirs in several countries, as well as the unequal distribution of geothermal resources in the world itself. The total geothermal heating is around 141 terawatt hours in 2021. This includes industrial heating, commercial heating, domestic hot water supplies, etc. So geothermal is one of the few renewable energy technologies which can be used both for electricity generation and heating applications. And we will see that the type of geothermal resource that is available determines to a large extent whether it will be used for electricity generation or heating applications. In India, the development of geothermal energy is at a very nascent stage. While there are certain geothermal fields that has potential, the commercial large-scale exploitation of this potential has not yet happened to a significant amount. So let's discuss the basic physics that is behind geothermal energy. If we go deep into the earth, the temperature of the earth rises steadily till we reach the core of the earth, where the temperature is around 6000 degrees centigrade, which is greater than the temperature at the surface of this earth. This energy and heat that is present at the center of the earth is partly contributed from the remnant heat that has not yet escaped from the time of formation of the earth itself, as well as energy generated through the radioactive decay of radiogenic elements like uranium, thorium, etc., which, being heavy elements, have greater concentrations near the center of the earth compared to the surface. The radioactive decay of these elements add to the heat that is present in the interior of earth. As we move from the interior of the earth outwards, the heat is transmitted through a mixture of conduction to the solid parts of the earth's interior, as well as convection in the liquid parts of earth's interior, which includes the mantle. And this heat transport causes a slow decline in the temperature as we move from the center of the earth towards the earth's surface. So for example, the temperature at the edge of the outer core is 4000 degrees centigrade. Temperature at the lower mantle is around 3000 degrees centigrade. Temperature at the upper mantle, where the mantle is hitting the earth's crust, is around 1000 degrees centigrade. And the mean temperature gradient through the earth's crust is around 30 degrees centigrade per kilometer. And if you see the mean thermal conductivity of the crustal rocks, this leads to a mean global geothermal heat flux of only 0.06 watt per meter square, which is a very small amount. This kind of shows that on an average, geothermal heat transport from the center of the earth is extremely ineffective and is not a suitable source of suitable thermal resource. However, at certain locations of the earth, due to the presence of surface anomalies, like there are boundaries between crustal plates, there are regions of mountain building activities or places where mantle plumes have come close to the crustal rocks, you can get much higher thermal gradients of 10 to 20 watt per meter square, creating heat fluxes and underwater reservoirs of superheated water, which can be used for geothermal energy extraction. So the basic thing that I want you to remember from this chart is that overall geothermal resource is very low and is not commercially exploitable. However, in certain regions, the heat source from the upper mantle can come very close to the crustal rocks due to various surface anomalies, and it is in these regions where the heat source is significant enough that commercial exploitation becomes possible. So this brings us to the geothermal resource types. Geothermal resources can be separated into two types: hyperthermal regions and semi-thermal regions. Hyperthermal regions are regions where temperature gradients of over 100 degrees centigrade per kilometer exist. These large gradients occur at the boundaries of continental and oceanic plates, as well as hotspot regions of the world where mantle plumes, hot molten rocks from the mantle, kind of rise up and thin the crust on either side. So here the near surface rocks are in active thermal contact with the convection currents of the upper mantle, where you can get temperatures of 1000 degrees centigrade or more. As a result, these are also regions of pronounced geological activity and surface instability. So geological activities here include earthquakes, volcanoes, mountain building, geysers and hot springs. In such places, hot steam and superheated water can be found just below the surface, and these can be used as a heat source. So there is something called a Lindell diagram, which shows that in the hyperthermal region zone, you can get superheated steam and water between 200 degrees centigrade to 120 degrees centigrade, and these can be used for geothermal power generation. So you can use them to create electricity. Then you get semi-thermal regions where temperature gradients are lower and around 50 degrees centigrade. These are not actually places where crustal plates and continental plate boundaries exist. However, these places are where there are local crustal anomalies like crustal faults, intrusions, rifts, etc. And such regions are also prone to earthquakes and can have hot springs and underground hot aquifers at reasonably high temperature, which can be tapped for geothermal process heat. So these are primarily used as hot water sources. So these here the temperatures are around 80 degrees centigrade to 40 degrees centigrade. Okay. So these are used for process heat applications. So in this figure, we see suitable locations for geothermal plants worldwide. This figure here is showing us the various plates that exist on the crust and the various plate boundaries between these plates. So here, for example, is the Pacific Oceanic plate. This is the North American plate, the South American plate, the Eurasian plate and the Indo-Australian plate. And you can see the boundary of these plates are regions where you can get significant geological as well as geothermal resource presence. So places like Japan, Indonesia, the islands of the Pacific, mountainous regions of Western America and Southern America like Brazil, Peru, etc. These are regions where significant geological resources are concentrated. Similarly, there is the mid-Atlantic ridge that is going to the center of the Atlantic Ocean, and Iceland is situated on the top of this ridge, and hence Iceland also has significant geothermal resources. The Himalayan region is a boundary between the Indo-Australian plate and the Eurasian plate, and here you have significant mountain building as in the Himalayas and also hot spring resources. And these can be used for geothermal energy generation as well. Similarly, the Mediterranean region is a boundary between the African plate and the Eurasian plate, and here also you get significant concentration of geothermal resources. So in this map to the right, the red regions are regions where high quality geothermal regions are more likely to occur than in other regions. So now let us look at the geothermal resource presence that is there in India. So in India, one of the main resource locations is of course the Himalayan belt that we discussed. And one of the most promising regions is the Puga Valley in Ladakh, where we have geothermal reservoir temperature of 180 to 260 degrees centigrade. Another place is in Uttarakhand, where there are hot spring regions close to Badrinath with expected underground aquifer temperatures of over 100 degrees centigrade. So these can be used for both hot water and electricity generation sources if they are suitably developed. Apart from these, there are other crustal areas where significant geothermal resources exist. For example, the Tatapani geothermal field is in the Son Narmada Tapti basin, this region here. And here also we can get underground aquifers of around 110 degrees at 1 kilometer depth. Then we have the Godavari basin in Andhra Pradesh and Telangana region, where the Geological Survey of India expects temperatures of 170 degrees centigrade in the underground aquifers. Furthermore, on the western coast of India, where there are significant oil resources, we also expect to have significant geothermal reservoirs in the Kangbe and the Konkan geothermal regions. So these are the locations where it is possible for India to develop geothermal heat and electricity applications. Now, how do we go about utilizing this geothermal resource? This figure shows an idealized map of how a geothermal resource exists underground and how it can be utilized. At the bottom is the magma or the heat source of the upper mantle, which is heating the impermeable crustal bedrock directly above this mantle layer. So this impermeable bedrock is heated up because of the presence of magma. Over this bedrock, there exists an underground aquifer, the green region here, where water from ground sources are accumulating through cracks which are slowly, water is percolating from the upper regions from rainfall, etc., and is collecting here in this underground aquifer. The water cannot go further down because this is an impermeable bedrock. So as the water rests on the top of this hot bedrock, and remember this water is pressurized because there is a lot of rock above it as well, and this water is not actually what you would say pure water. It has a lot of salts, etc., and is primarily present as within a kind of a porous rock structure. Okay, it's not just it's not a vast underground cavern or anything. There is a pressurized porous rock structure, and the water is existing in this porous rock structure. Okay, and because the rock is hot, the water also gets superheated. Okay, it cannot convert into vapor because the pressure is significantly high. Okay. Above this is the permeable rock structure through which the water has percolated, and above this you have the impermeable cap rock, which is basically the ground rock structure that is existing. Okay. Now, what usually happens in a geothermal region naturally is that there are certain fault lines on this rock structure, and the pressurized water can often take advantage of these fault lines and move back up and create hot springs, fumaroles, and geysers that are often present in these geothermal regions. Okay. What we do when we want to extract a geothermal resource, for example, for electricity generation applications, we drill down to this underwater hot aquifer. And as we drill, once we reach the aquifer, this pressurized water, heated water, rises up through the well, and this is collected at the top of the drilling rig. If the water is hot enough, part of it is directly converted to steam, and the steam water mixture is then transferred through a series of pipes into your electricity generating unit, which is usually a normal steam power plant. So this hot water converts into steam, and this steam, because the pressure is reduced, and this steam is piped to your steam power plant to run your steam turbine and generate power. Then the condensed geothermal fluid is injected back into the aquifer through a reinjection well. This helps to keep the aquifer recharged so that the water in the aquifer does not go down. So we use the hot heat and then re-inject the water back into the well to get to keep the aquifer from emptied out. So this geothermal fields therefore contain an extensive system of boreholes and pipes whose construction and maintenance is the majority of the plant cost. Okay. Because like drilling these wells for the uptake of geothermal fluid and the re-injection of geothermal fluid, and the entire system of pipes that is transmitting the fluid to your steam power plant under insulated conditions is the largest capital cost for these kinds of systems. Another important thing to note is the re-injection not only helps keep the aquifer recharged and so that the water level does not drop, but also it's a safe and sustainable way to dispose of the hydrothermal fluid, which often contains heavy metals and otherwise will pollute the surface water. So this hydrothermal fluid is basically a type of brine, and it contains high amounts of dissolved salts like sodium chloride, potassium chloride, calcium chloride. It can also contain dissolved gases like carbon dioxide, methane, hydrogen sulfide, as well as trace amounts of radioactive elements like radon. So if we are just keeping it on the surface, there is a chance that it will contaminate the groundwater reserves that are here, and that will pollute our ground. So re-injecting them in the well is a sustainable way in which this can be used without causing pollution to the environment. So we will stop here today. In the next class, we will look at the various types of turbine systems that are used to actually process this geothermal fluid and convert it into electricity. So thank you for listening, and we will meet again in the next class. Thank you.